You Hello, hello, hello. Good evening, good day, good morning, wherever you are in the world again. Ooh, my mic's a bit too loud. Hold on. Check. I think a little bit more. Alright, so let's try that again. Okay, I want to hear myself real quick here. And now I just adjusted to full. Now let's see how they sound. Hi, yeah, it's a bit too loud. So let's get that up, down, or rather. So hello again. Let's get that up. Hold on, then I'm gonna show myself. Okay, hello, hello, hello. Good morning, good day, good afternoon, good evening, good night to everyone, wherever you are in the world. And welcome to an open stream. Today, yeah, we have an open stream today because unfortunately, the student for today is feeling under the weather, so we were not able to meet today. We're not able to meet today. Um, so Ariana, if you're listening into the stream later, get well soon. Why am I picking my nose in public? All right. Now let's just check if anyone's online. And let's do the other one too. Oh, somebody's on Twitch, I think. So for now, I unfortunately because of that, Ariana's not around today. I don't have anything to teach actually. So what we'll do is we'll just while we don't have any students here, I'm going to just rant. Well, rant about physics and math and science in general. Yeah, I'm not gonna rant about whatever. Or okay, let's see. Okay, since there's no one around for now, here's an idea. I'm going to hold on. Still no one on the chat. Okay, so anyway, this is what we'll do. We'll go on the board. Let me just fix this. And let's get the calculator ready as well. Okay, so what's going on in freaky physics? Well, first of all, in fact I want to show you something. Okay. Okay, if you cannot see that on the screen, well, I am hold on. What's happening? Oh, the internet's just slow. So the first thing is what have I been doing? I've been basically doing this. Okay. Uh Let me adjust this a bit so you can see that properly. Let's remove the crop for now so you can see that properly. Okay, so as you can see, well, this website's been up for a while, but today it is full of stuff that you can actually go through. What I've done here is I put all the playlists here that we've made so far from the streams. So we have the momentum questions, we have the imaginary numbers, we have the table technique, its own playlist, and then solving physics problems on ramps. All of these are here. Now, of course, you can see here the website is freakyphysics.xyz. I used to own the .com, just so we're clear. Yeah, I used to own the .com, but when I just totally forgot to renew the subscription 1 year. Like I forgot for like I don't know 2 months. That's on me. Don't worry. It's not on the provider or anything. That's on me. I forgot. Totally forgot that I should have paid. So when the domain became open to everyone to buy, somebody snatched it up, somebody from China, and put something in there, and I couldn't get it back. So here I am with the XYZ URL. Okay. So again, don't forget it's freakyphysics.xyz, not .com. Okay, freakyphysics.xyz. And if you continue, I've already put here how you could follow, either watching through this live stream. So our options are Facebook, YouTube, and Twitch. Social media for followings. So announcements will be done on Facebook. Twitter, yeah, we do have a Twitter. I forgot I had a Twitter, but it's being used. It's still active. So, well, correction, not Twitter. It's now X. Okay. All of the naming controversies aside, yeah, Twitter's here. Of course, there's TikTok, there's Instagram. For tutoring, I just put it here, my tutoring link. So if you do tutoring, it's here. And of course, Patreon is already up. So you can support us through Patreon. But for now, I haven't set it up properly yet. I've just put it up here for reference later on. Of course, we have our posts. This includes the ones we've just seen earlier. So that's everything that I've posted about the shorts. And then we have some old articles. Unfortunately, I'm not able to migrate all the articles I've written before. So far I only have 1, 2 articles up here. Okay, we actually have a few more, and that's at the very bottom. You can click on the following things. Oh, I don't think you can see that here. Yep, you're not able to see that here. So let me move this a little bit. There we go. Like that. Okay. So we have a couple of places you can go to. You can go to the YouTube lessons here. These would link straight into the YouTube channel, and so will this. These two buttons lead straight to the YouTube channel, one for the long form live videos and one for the shorts. Okay, and then on the second set here, these would link to blog posts in this very website. I'll show you an example. Let's open one here and let's open the misconceptions here. Okay, so under misconceptions, again, there's only one that I've been able to migrate so far. This is a very common misconception. I think I'll go through that briefly. And then we also have this. Again, I've written a few. I've only been able to export 3. Which one's my favorite? This is my favorite. Let's open this. So basically, this question is about how much does an Instagram weigh? How many grams are there in an Instagram? If there are 1,000 kilograms, 1,000 grams in a kilogram. So, long story short, there's a bit of an explanation here, and then here is the calculation. Just move that a bit. So the calculation basically says it's not big enough yet, so let's adjust that further. There we go. So yeah, one Instagram, according to this calculation, is around that much, that heavy or that massive. Okay. Um, I want to point out this bit, the for comparison bit there. Okay. Um, I want to focus on this bit. Another way to look at it. So if you compare a flea to like the largest ships in the world, a flea is only 10 to the minus 15 orders of magnitude smaller than a ship. Okay, so this compared to a phone, this would be approximately 10 to the 20, 10 to the minus 19. So it's still much smaller. So the mass of an Instagram is basically negligible, but it does have a mass. Okay, there are other ways to look at it. I think I'll revisit this one day. But of course, a lot of the things here is there is an application to that nonsense. Okay. All right. So the other one, let's go to misconceptions. Let's open that. This is a really common misconception, and I'm gonna go through this. So okay, let's just fix the screen so you can read that along with me. Okay. So for now, there we go. So you've seen it in movies, you've seen it everywhere, as you can read here. Basically, you all have experienced it. Excuse me, you've all experienced it visually. There is no gravity in outer space. At least it seems like that, right? But the problem is it's only all visual. Okay, the thing here is there is always gravity all over the universe, no matter how far you are from anywhere. Okay. Um, okay. Basically, what we're gonna look at here is Newton's laws of motion. Newton's laws, just so we're clear, um, they work at least for this little bit of for the bit of physics that doesn't really involve extremely large masses like black hole sized masses or extreme speeds comparable to the speed of light. So what is happening here? Newton's laws of gravitation, this equation right here, this equation right here. Okay, that didn't highlight. So this equation right here is the equation that Newton came up with. The negative here, let me explain this briefly. The negative here means that gravity is always attractive. The negative is placed there because in order to make this consistent with electric charges, which we will be looking at soon, I think we've done this with another student of mine with CJ. So here, this negative simply means that gravity is always attractive. G here is not the 9.81 that you're used to if you're in the lower levels of physics. This is the gravitational constant and it's a tiny number. It's not given here, okay? The two m's here are the masses of the two different objects, and the r is the separation distance. Let's go to that diagram there. By the way, that's Isaac Newton right there. The here it's a different form. It says d right here instead of r, but the idea is still is the distance from the center of one object to the center of the other object. This center is the center of mass and not the geometric center. Okay, basically if you can focus all the mass of an object onto a point, that's where it is. That's the center of mass. Okay, so going back to the equation, what's the key idea now? If there's gonna be a spot in the universe where gravity is zero, we can expect this, that we can get zero on the other side of the equation. That means one of those other terms on the right side must be zero. So I'll just go through this with, I'm not going to read through this anymore. I'm just going to go through. This g has a value. We've determined its a value. It's not 0. Otherwise, it will always be 0. Gravity is always going to be 0, right? So the next bit is the masses. If something exists, at least in Newtonian physics, these must also be non-zero. So the only zero component must be, let's go down, the 1 over r bit. But the problem with the 1 over r bit is that the only way that can be 0 is if r is absolutely huge, infinitely huge. And in the universe, that cannot happen. So this can never also reach 0. So if we put the math in, so 0 would be equal to some non-zero value, so that's not possible. So we can therefore conclude that there's always gravity everywhere. Okay, but of course, that's the misconception. So let's see what the actual idea is. Okay, now why do people have this misconception? Very simple. Whenever you see an astronaut in outer space, it seems that they're floating around. That's what it seems like, right? Okay, but here, this is basically how much an astronaut would weigh up there in the International Space Station. This 1,427 newtons. This is assuming that the kilogram with his equipment has a mass of 150 kilograms. So basically, it's still saying it's still pretty close to the actual weight a person would have near the surface of the Earth. Because the shortcut, we all know the shortcut. Well, most of us would know the shortcut. If you know the mass, the shortcut is you multiply the mass by 10, and that would be your weight on Earth. So this astronaut with all the equipment having a mass of 150 kilograms would have a weight of approximately 1,500 newtons. Look at his weight in the International Space Station. It's pretty close. Yeah, it's pretty close, which makes it weird. So the idea here is that weightlessness is not about the loss of weight. The sensation of weightlessness is not about losing the weight. Okay, I'm gonna go straight to something that all of us would probably have experienced. We've all been in an elevator, right? And what happens when the elevator is, well, not really going down, but it starts moving downwards? Let's take a look at that first. If it starts moving downwards, you feel a bit lighter. It's like you feel like you don't weigh as much, at least for a split second, right? For a split second, you do not weigh as much. The idea there is because if you think about it, the elevator is falling not just at the same rate as you would if you were just under gravity, right? So imagine, what if the elevator was moving? What if you were falling and the elevator was falling? Right? So the idea here is actually that I want to highlight this bit. That particular idea is similar to what Einstein used to come up with general relativity. Okay. It's explained here further. In general relativity, it's this. Basically, if you were in a container and you're standing in it, can you determine whether you're on the free Earth surface or accelerating upwards? Okay, there are a few videos on YouTube for explaining this, but you can see here I have a few images. Now, this is an interesting image right here. Okay, you see there are people like floating around. This is not a trick shot. These are not people jumping. These are people actually floating. But then again, as we said earlier, you wouldn't really know if you were falling if the container was falling with you, right? So in this case, these people who are floating are actually falling. It's just that their container, which is an airplane, is also falling. Now, here's the thing with the airplane. The airplane is controlled. The pilot's really, really skilled, okay? They make sure that when you fall, the airplane actually also falls. So the airplane has to kind of like take a dive. Hmm. So here are a few videos. I'll play this one. I think some of you may have seen this video here. Okay. The zero gravity here is not, again, the actual absence of gravity. Let's kind of put the... I think that's better. I think that was a bit... I think that was a bit too loud, but here. There. That's not really zero gravity because they're falling. But because, again, like I keep saying, it's not really zero gravity. They're just falling. It's just that the airplane is also falling. Either way, this is an awesome shot. Okay. Alright. I'll pause that for now. Alright, so that's the idea. When something is falling, when you're falling, and then the container is also falling, you will experience quote unquote weightlessness. Okay. We've discussed this a little bit. So basically, how about up there? What's happening? It's the same idea. The International Space Station is falling. You are also falling with the space station. Okay. There is another way to look at it, but for now, we'll keep it like that because the other one requires us to know something about circular motion. Well, you know what? I'll get there soon. Later. All right. So you may think, wait. What about an astronaut who's outside? There is no container. He should fall to the earth and die. Right. So let's get okay, let's get to the board first and let me change the settings back so we can. There we go. All right. So what if you have an astronaut who is actually outside the space station? Why doesn't he just fall to the earth? The question is actually flawed. Yeah. The idea here is the astronaut is falling. But I'm gonna change that. Okay. What is falling? Falling is simply moving towards the center of the earth. Well, it's not only earth, but for our reference, we'll use earth. Okay. So what do I mean? If we draw the earth, and this is the earth, that's the center. If you have an object here, it's gonna fall that way. And of course, it's gonna get stopped by the earth's surface. If your object is here, it's gonna go that way. Same thing. If the object is here, it's gonna move that way. Okay, so we've established that, right? But there is something missing in this case. These objects are assumed to be motionless at the beginning. Okay, so these objects are assumed to be motionless at the very beginning, and therefore they actually fall. But what if, let's just take, you know what, I'm not going to draw the Earth as a sphere yet. I'm going to draw the Earth as a flat surface for now. In fact, that flat surface is going to curve a little bit like that. Okay, let's say that you have your object here. If this object was motionless, we know it's going to fall that way. Okay, but what if instead of being motionless, our object, why are fireworks being shot today? I can hear fireworks up there. Oops. All right. So okay, I'm getting distracted by the fireworks. Let's go back here. So let's say that your object, you're actually throwing your object a little bit like that. It's so what will happen is I'm gonna draw the original downward path up to here. It's now gonna fall a little bit curved, right? Now, what if I increase that? What if we increase the speed at which that, so I'll label this, this is the speed at which the object is moving horizontally. So in this case, this particular object will probably be moving in a curve like this. You increase the speed, what happens? We're gonna use this now. The more it's gonna do that. You get the idea. If you get the idea, what's happening here? The the horizontal speed of an object will do what? Make the object follow a curved path while falling. Okay, this is the key aspect in falling without the container. Why you're still weightless. Okay, so it makes sense. So in this case, if we're gonna draw the Earth as a sphere now, or as a circle in this case, that's the Earth. So that's the Earth. And then you have your object that's here. This is your object. So basically, again, if we follow the idea, it could curve, it could keep curving like that, right? And then eventually, there must be a path. There must be a path that goes around the Earth. It falls to the Earth, but the curvature of that path is just enough for it to miss the surface of the Earth. Okay, so an object that falls towards the Earth but is moving at a certain speed compared to the Earth's surface is gonna follow this curved path. Okay, so so I'll put that here again. Hold on. So there will be a curved path that will miss the Earth entirely. Or not just a curved path, there will be some curved paths. Okay, entirely. Okay, specifically, I'm gonna erase these other ones now. Okay, okay, I'm gonna erase these other paths. There will be the most simple path that the object can take is a circular path. Okay, so it could be a circle. It could be an ellipse, or for example, something like this. Okay, could be an ellipse. Okay. There's another possible path, but that doesn't loop around. So these are the two possible paths that will miss the Earth entirely. Now, in both of these paths, you will feel weightless because you have nothing to touch. You have, uh, yeah, you're still falling, especially on the ellipse. You could actually see that on the ellipse, you're still falling, right? And the thing is, this is the path that most satellites follow. But if they really had, if they really were falling towards the Earth without any some sort of forward speed, then they would hit the Earth, no problem. But the thing is, because they have that bit of a forward speed, they keep falling towards the Earth, but they will they will miss each and every time until they just slow down enough to, you know, start spiraling into the Earth's um, atmosphere, then crashing into the Earth. Okay. So anyway, this particular part here, wherein you just miss the Earth, these are your orbits. Okay. Again, the most simple kind of orbit is the circular orbit, but most orbits, most natural orbits are okay. Most natural orbits are elliptical. Okay, so go. Basically, there's no gravity in space is wrong, but gravity does not no. But the let's say it like this: the presence of gravity does not necessarily mean you feel weight. You still have weight, but you don't feel it. That's the key idea. Okay, and what makes you feel it? It's the contact with the container. In our case, here on Earth, our container is the Earth's surface, or you know, your chair, the floor, whatever. In outer space, your container would be the space station. In the airplane earlier, the airplane is the container. So, what do the containers do? The containers provide what's called a contact force, and that contact force is the thing that opposes gravity, and that's the thing you feel. Which again goes back to the elevator. When the elevator drops, the contact force decreases. That's why you feel lighter. It doesn't totally disappear, so that's why you still feel your weight. Okay. All right. So yeah, that's a bit of something from the. Anyway, that's a bit of something from the website. Yes. So we'll go back to the main page. Let's go back home. So these are just a few of the things that you would expect from here. Again, we have these things. I'm gonna show you one. I think I'll open the table technique from one. Because that's got like, I don't know, not really the most. I think the one with the most videos is the ramp problem. Anyway, let's open the table technique. Okay, so you see there's a description of what skills and things you're learning here, the methods that I'm sharing, and of course the actual video. Oh, if you want to leave some comments, please do so in the YouTube comments, not here in the website. I made sure that there are no comment sections here. There's no comment section here. So comments, please leave them in YouTube. That way, you help engage with the channel, and therefore we get more views, we get better quality videos later on. Okay. So anyway, okay, this is what the okay, like I said earlier, this is a playlist. I'm just gonna mute this. All right, so each of these, in this case, we have 3 videos. Let me turn off the filters again. Hold on, let me turn that off again so you can see that. Okay. So when I do this, okay, you see that there are 3 videos into this playlist. So once you've seen the first video, basically depends on how many videos there are in the list, but those 1 hour videos, these 1 hour live videos that we were doing, they can be condensed very easily into like 10 minutes worth of content. So in this case, this whole thing was condensed to 3 minutes of content, and they were turned to shorts. But of course, the shorts are still pretty useful. Let's put that to full screen. Okay, let's put this to full screen. Okay. And then, as you can see, these automatically play. Wonder what you can actually see on the screen. Hold on. Ah, you can see the. You don't see the whole thing. So there. And then right now, there. This is another short, 58 seconds. And then let's just click to the end for now. Then it's gonna go to the next bit. Okay. Now here's a better set of shorts. Let's go back. I think this one, the ramp problem was much better in terms of the quality of the shorts. Let's put that in full screen. Again, you can see here 9 videos in total. So this particular 1 hour lesson was condensed into 9 minutes. Remember, each short is about a minute long. So yeah, this is basically how the website goes. Okay, so let's put the thing back on. And let's put this back here. Okay, so the TikTok and Facebook shorts, they're there just to be there, but they're not actually. I'm not trying to monetize off of them. If I'm trying to monetize anything, it's these shorts. Oh, I just remembered. Yeah, TikTok also helps in monetization. Instagram's the one that doesn't really help. But yeah, Instagram, Facebook, and Twitter, they're mostly for engagement with audiences, like announcing when streams are and everything. But the videos themselves will be found either here on YouTube or on TikTok. The long form is definitely on YouTube and the other streaming platforms. That's Facebook and Twitch. Yeah, Twitch. But the shorts are uploaded here on both YouTube and TikTok. All right, so let's go back home. So here, okay. So anyway, just want to explain this. The tutoring under Preply, I've currently suspended it just because I have way too many students at the moment. Yeah, I'm popular. With tutoring, at least I'm popular. So, uh, okay. I think I have an idea. I think I'll be showing you just some testimonials from Preply, but I gotta get away from the screen first. Hold on. So how long have I been teaching in Preply? I've been teaching in Preply for about, I think this is my second actual year. Yeah, my second actual year of teaching. I've been a member of Preply for like 4 years, but I got my first student 2 years into getting to Preply, and then uh, my first student led to the second really fast, and then snowballed from there. And I am getting a lot of students. I'm not sure it's because of the amount I charge or because how good I am, but I've not lost a student to other tutors just yet. I've only lost students because either they've graduated and they've gone to university, or they really couldn't stay with me due to time zone differences, uh, or finding somebody who can do it offline for them. But I've not actually lost a student to another tutor on Preply, so that's a good thing. Um, Let me get to my, hold on, profile. I'm not showing you the entire profile, but yeah, you can click on it in the website later on the Freaky Physics website. Uh, okay, I'm trying to look for my profile here. That's weird. I can't find it. That's it. Okay, give me a moment. Okay, I think I'll just put this up onto my normal screen first so it's easier for me to work with. Yeah, that's a lot easier. There we go. Okay. Okay, hold on. Let me show you, and I need to not show this bit. Okay, there we go. So, alright, so here's my Preply profile. I'm not showing you all the things. The rest of it you can see later on by yourself. Oh, by the way, if anyone's listening here who are my actual students, remember if you do this, I will not accept you simply because it's just a conflict of interest for me. I want to play it safe, so I hope you understand. If you're not one of my students in school, though, you're more than welcome to do this. But anyway, you won't be able to do this now because again, I've hidden my profile because I have too many students. So let me show it to you now. So that's my Preply profile right there. Let's just go straight to the 8 out of 8 rating. I don't have that many students simply because uh, yeah, I pick how many students I can have at a time. It's not that I pick the students, but I pick how many. So this is the latest one, CJ. He's in. So okay, a bit of a background for CJ. He started off with 2s and 3s as his grade in IB. Now he's getting 5s and 6s. He got a 6 on one of his tests last time. Okay, he still struggles, but he's doing much better. So thank you, CJ, for your kind words here. This was a former student. Okay, I'll okay, I break them explain them thoroughly. Okay, right. Here's another one. Um, Adam. Adam also was a struggling student. He's already graduated from me, so I think he's in college now. He also, at least, he gets concepts rather quickly, but still, here's the thing about me. I don't believe that it's all me. I still believe that it's partly the student as well. If the student is more than willing to put in their share of the load, okay, then yeah. Modular arithmetics. Lemari Pata. Hi. Do I understand modular arithmetics? Kinda do, but it's been a while since I taught that. I may need to refresh myself. All right. So yes. Okay. Do you? Anyway. So while I'm waiting for the rest of what you want to say here, I'll show some of these testimonials. So okay. Destin. Yeah, he was one of the ones I lost due to time zone differences. It's too early for me and too late for him, so we decided to part ways. But I looked for a tutor for him that would be better for his needs. Ryan, I remember this kid. He he was wait, let me try to recall his grades back then. When we started, he said that his grades were like ones and twos. Again, this is IB physics. He ended up getting a 5, which was way higher than he expected. But I did tell him that even though it was a 5, I was actually expecting him to get a high 4, so a 5 was not out of the question for him. Okay. This Lynn. This is the parent's name. Student. Okay, the student here is when I met him was an 8-year-old kid. So it's gonna be 9. I think she's 9 now. Okay. Uh, Basically, yeah, this is the best written testimonial here. So yeah, I really thank. Okay, so anyway, thank you for those kind words. Okay, Kartik's one of my first. Again, I lost him due to time zone differences, I think. And then Rio was just in for consultation, so he was in with me for 2 lessons for consultations, but still, from what I heard, he did well from with what he consulted me with. Okay, so anyway, now let me close that and wait, close. It is not closing. Okay, let me just stop there for now. What just happened to my board? Okay, there, fixed it. So let me fix that as well. Okay, so Lemari Patah. Well, okay, first of all, Lemari Patah, that sounds so Indonesian. Are you in Indonesia? Or maybe Malaysia? Well, modular arithmetic. Basically, okay, what I can do right now, because I don't have anything else to do, to say, and at the same time, I don't know what exactly is the particular topic modular arithmetic there is that we need that you need. So what I'll do this briefly. Let me pull something up here. Mm-hmm. Okay, but basically for those who may have heard about this for the first time, what's modular arithmetic? Okay, there are two ways to look at this. I like the second one better, just over here, because that's actually how the one who came up with who came up with this, by the way, Carl Friedrich Gauss. Gauss. Okay, so I'm just gonna say Gauss. Now, for those who are familiar with him, yeah, you know what he did. For those who are not, he's basically one of the big names in math. He came up with a lot of different ideas, and he's a math genius. He was a kid. I think he was like in 3rd grade. The story here is this before we go to modular arithmetic. The story here is that when he was in 3rd grade, okay, his teacher, because his teacher was bored, and you know back then teachers don't teach like now, like they try to explain everything, they give you different activities to see if you understand and everything. Back then, teaching was the teacher would write on the board, students were expected to just write and be quiet and everything. But anyway, during 3rd grade, his teacher ran out of stuff to teach and he got bored and there was still time. So what he did was he asked to the class, not just Gauss, yeah, but the class. He asked the class to find the sum of 1 plus 2 plus 3 plus all the way to 100. So he asked the class. Okay. His classmates did this. 1 plus 2 is 3. 3 plus 3 is 6. Something like that, right? But of course, not in that manner because, at that time, you were really supposed to even do it the long way, which is 1 plus 2 plus 3 plus 4 plus 5, then and so on, all the way to 100. You know this method, so or rather, something like this. Oh yeah, something like that. But Gauss, the genius that he was, because even back then when he was a kid, he was already a genius. He found something out. But instead of doing it in order, he did it like this. I'm gonna add the plus 98 plus 99. Okay. What he did was he added these. That's 101, right? Then he added these two. That's 101. And then he added these two. Again, that's 101. And so on. So he noticed that there should be 50 pairs of these. So all he did was 101 times 50. And that gives you 5,050. So when he turned in his work within a minute instead of within an hour, his teacher thought he was cheating, but no, he got it. He got the answer right. Genius, right? So anyway, what is modular arithmetic? Okay, so let me erase this because I'm ranting too much here about Gauss. What is modular arithmetic? Two ways to think about this. Okay, the first one is that modular arithmetic is what is if you have two numbers A and B. Okay, the proper way of thinking about this, and this is the way that I prefer, is that okay, actually no, let's start with a with a more intuitive but more difficult idea. Okay, the more intuitive here is if A divided by B gives you a number. So let's do it like A divided by B gives you some number C plus a remainder, right? This remainder is called the modulo. And this modulo is what gives the modular arithmetic its name. Okay. The other way of thinking about this is if you have a circle of radius A, circumference A. Circumference A. And then you have a line of length B. Okay. If B is wrapped around A, if the line is wrapped around the circle, so I will have to type this in. So this is the key idea. If the line is wrapped around the circle, how much rope, how much of the line is left over after wrapping the circle a complete number of times. Okay, so that's the key idea of modular arithmetic. In case you still cannot visualize this, let me get some circle here. Do I have something circular here? Yes, I do. Where is my pen? Okay, this is the last thing we'll do today for the stream. The modular arithmetic. Modular arithmetic is about, okay, so I like trains. Hello. This is about basically looking for a remainder. Whoopsie. What grade? Usually you learn about modular arithmetic either in higher level high school. So if you're in the US, this would be in your APs, AP math, or in university level math. But this is the key idea. But anyway, that's the key idea of modular arithmetic. Okay, what's this for? There are several branches of mathematics which are best answered using modular arithmetic. Okay, so here's an idea again. So let me get back to full screen, and this is where this is gonna be the last thing we'll do today. Uh, Let me get to the main screen. All right, so again, so we have my pen here, which has a circular cross section, and I have what's the best thing I can do here? Okay, I have a rubber band here that's been snapped into. That's been, not snapped into, but snapped. So it's now not a band. Okay, so what's the idea? You're gonna wrap this thing around the pen. So here, I'm looking at it, it's wrapped once. It's now gonna wrap not quite twice. So the modulo here would be this. Okay, so the entire length of the band is, let's get rid of the pen. The entire length of the band is this much. I hope you can see that. Okay, that much. There's the end. Now, if you wrap the wrapping earlier, if it wraps around completely, it should look like this. If it wraps around completely twice, the ends should go meet each other when they go around like this, right? But earlier, they didn't quite, the rubber band didn't actually quite make it all the way full. So the modulo here is the remainder. This little bit here is the remainder. This is the modulo. Okay. Pink sheep. Well, thank you for the words. Thank you for the kind words. Okay. So at the moment, that's basically it. That's all I can say about modular math or modular arithmetic, because it is quite high level math actually. Even though it seems simple, it's quite high level. um, okay, why is it high level? Because it may start with a remainder, but once you get into like the math, doing the math with the modular math, yeah, there is something. Well, I'll just show you a quick preview of the Wikipedia page just to show you what I mean. Okay, this is basically the same idea like I said. So another way of looking at it is clocks, right? Your clocks go around once every 12 hours. The hour hand goes around once in every 12 hours. So 13 is modulo 1. Why? There is a leftover. If it goes around 13 is you're gonna go once around the clock, and then you have an hour extra, so to speak. So 13 divided by 12 is modulo 1. Or another way of saying it is okay, there. 38 is 14 modulo 12. Here's the example. Oops, sorry, I'm not in the screen. So here's an example. Ew. Hold on, let me put that on the screen. Okay. Let's put that there. Okay, so I'll show you what that looks like. Okay, see, it's very simple. Um, it's simple to start with, but you see the math. The math here is kind of easy still if you understand what's happening here. Basically, what's happening here is that two integers are congruent modulo m if m is a divisor of their difference. Okay, basically the important thing here is the difference. Okay, another way of doing that is this. Okay, now I think I'm gonna give you the example straight away what this means. This. Okay, what does this mean? Okay, what is 38? 38 divided by 14. Okay, okay. Uh, Here. So not 13. 14 modulo 12. Okay, modulus 12. The idea here, let's go to more simple number first. Let's go to this. What is 8? Why is 7 modulo 5? Negative 8. Because if you take 8 and you add 7 to it, you subtract 7 from it, that's 15. Right? So negative 8 minus 7 is negative 15. And that means if you divide, you see it's a bit confusing. Even I'm still getting confused with this. Right. But anyway, that's the idea. It's all about divisibility. So the idea here is I have negative 8. I subtract 7 from it. It's going to give us negative 15. And that means um, if you divide either number by 5, is that the idea? Hold on. Let me see. Yeah. So you get this, you take the difference, and whatever factors there are in that number, that would be the modulus of that number. So we can say that 8 is 7 modulus 3 as well, because 3 times 5 is 15. And 15, well, negative 15 in this case, is the difference between 8 and 7. Okay, same thing here, 38 minus 14 is 24. 24 is, 24 is 2 times 12. So it's modulo 12, definitely. Why is it not modulo 2? Modulus 2? Simple. They're both even. They're both even. Yes, 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 Jolly Knight. Yes, that's true. However, at this point, like I said, it's been a while since I've done modular arithmetic, so I can't really help you with finding that particular answer. Okay, so, okay. Oh, it's beyond the time, and I have to get ready for another class. So, I'll just talk about this last one here. Okay, 22 factorial over, well, let's just write that. That's an interesting problem. 22 factorial minus 1011 factorial divided by, is that 1010. Okay. Okay. Yes, it can be solved with modular arithmetic. Let's try. I'm gonna try to solve this without modular arithmetic first. This is gonna be this. Well, don't forget the factorial. Okay. Then this is gonna be, there's a minus 1 here. This will be 2022 factorial over 1011 factorial. You see how difficult it is without modular arithmetic? We're just going in circles. 1010. This is going to be 1011 times 1010 times 1009 factorial divided by 2022 factorial over 1011 factorial minus 1 all over 1010. The 1010 cancels out, so good. And then this 10, 11, and this 10, 11 cancels out. This becomes 10, 10 factorial. Oops. Okay, but from there, where do we go? We get stuck without modular arithmetic. So we need to solve it with that. Okay. Alright, so anyway, we'll end the stream here so I can get ready for my next class. Thanks for stopping by, everyone. And okay, so again, just like before, I wish you all a good evening, good day, good morning, good afternoon, wherever you are in the whole wide world. Okay, I will not say your name. I'm not really a math teacher, I'm a physics teacher, but you know, yeah, you can't really do physics without math. So I'm familiar with most math, but I need to review certain topics. Anyway, so like I was saying, yep, good night, good morning, wherever you are, good afternoon, wherever you are in the world, and thank you for stopping by. Stay freaky, everyone. Bye bye now. Oh, before that, don't forget, follow us on these. Okay, and one more thing before I forget again, for those who are new or just who just came in, don't forget, follow us on freakyphysics.xyz. This is we now have stuff here. If you want to go through that, go ahead. Again, the website is freakyphysics.xyz, not .com, alright? Okay, so with that, really, bye everyone, stay freaky.